In this chapter, we study the electric vehicle routing problem. The goal is to design delivery routes that are not only low-cost but also feasible under battery limitations. Electric routing adds a new operational layer. Decisions about where to drive and when to recharge are part of the plan, and a route that looks short on a map can still fail if the vehicle cannot complete it safely. This slide summarizes the core objective. We want minimum cost routes that serve all customers, but we must respect the realities of electric vehicles. Battery range, charging time, and charging station availability mean that feasibility is a first-class requirement. In practice, dispatchers need methods that protect service reliability and prevent vehicles from being stranded. EcoHaul is a logistics company transitioning its city fleet to electric vehicles. This reduces emissions and fuel costs, but it changes daily routing operations. Dispatchers now need routes that incorporate recharging decisions. The plan must account for where charging stations are, how long charging takes, and how operational conditions influence energy use. Electric routing is hard because the system has coupled constraints. Distance alone is not enough because energy consumption and charging requirements determine feasibility. Charging adds time and can create queuing risk. A robust routing plan must coordinate customer order, charging stops, and buffer margins to avoid infeasible outcomes. This chapter uses a tiered toolkit. Tier 1 builds a complete mixed integer programming baseline. Tier 2 uses a modified savings heuristic for scalable construction. Tier 3 explores global search using a Dragonfly meta-heuristic. Tier 4 learns a policy using deep reinforcement learning. Tiers 5 through 9 expand to digital twins, autonomy, human and artificial intelligence collaboration, ethical objectives, and quantum formulations. Tier 1 provides the formal baseline. It decides which arcs are traveled and tracks the battery state and time progression. This matters because feasibility in electric routing must be guaranteed by design. The model makes explicit which decisions create feasible routes and which decisions cause battery failure. This slide defines the core sets. We model nodes as customers, charging stations, and the depot, and we track a set of electric vehicles. Operationally, a node is a place where a vehicle can travel to, and only charging station nodes can add energy. This distinction drives the feasibility of a route. Parameters describe the physical system. Distances and travel times define movement costs and timing. Energy consumption defines how battery state changes when traveling. We also define the maximum battery capacity and the charging rate. Service time at customers captures the reality that deliveries take time, not just driving. The decision variables include a binary routing decision, the battery state upon arrival time, and the energy added at a node. These variables connect routing decisions to energy feasibility. Without explicit battery and charging variables, the model would produce routes that are short but physically impossible for an electric vehicle. The objective minimizes total travel distance across all vehicles. This is a natural baseline cost measure. However, cost minimization is only meaningful when feasibility is enforced. The constraints that follow ensure that the chosen routes can actually be executed with available battery and charging options. The constraint section is shown in full so the Tier 1 model is implementable. Each constraint corresponds to a specific operational rule. As you go through them, focus on the purpose of each rule: customer coverage, route continuity, depot usage, battery balance, charging feasibility, and time progression. Each customer must be visited exactly once. This is the basic service requirement. Operationally, it prevents both missed deliveries and duplicate visits that waste distance and battery. It also defines the coverage target that the routing plan must satisfy. Flow conservation ensures route continuity. If a vehicle arrives at a customer or charging station, it must also depart in a consistent way. This rule prevents disconnected route fragments. It is essential for producing a continuous path rather than a set of unrelated arcs. Each vehicle can leave the depot at most once. This controls route initiation. It prevents solutions that artificially split one vehicle into multiple disjoint tours. It also supports the idea that a vehicle follows one primary route for the day. Routes start and end at the depot. The constraint ties route departure and return. Operationally, this matches the daily reality of fleet operations where vehicles begin at a depot and must return for charging, parking, and the next day reset. Battery consumption links travel to energy feasibility. After traveling from one node to another, battery state decreases by the energy required for that trip. The big constant term is used to deactivate the battery rule for arcs that are not selected. Charging energy is added only when the vehicle actually visits a charging station. Battery bounds enforce that state of charge stays between empty and full capacity. This prevents two failure modes: negative battery, which corresponds to running out of power on the road, and overfilling beyond capacity, which is physically impossible. Charging is not allowed at customers or at the depot in this formulation. Only charging stations can add energy. This reflects operational policy and infrastructure limits. It ensures the model does not create unrealistic recharging at delivery points. Charging amount is limited. A vehicle cannot charge more than the remaining capacity to reach a full battery. This rule prevents the optimization from using charging variables as a mathematical shortcut. Operationally, it represents the physical constraint of battery capacity. Time evolution captures how arrival time increases. It includes service time at the current node, charging time at a station, and travel time to the next node. This makes the plan usable when timing matters, such as when drivers have shift limits or deliveries have time windows. It also makes charging a time decision, not only an energy decision. This figure provides a small illustrative network with a depot, 2 customers, and a charging station. The key lesson is feasibility. The routing plan must ensure that the vehicle can travel between consecutive nodes without running out of battery, and that charging stops are positioned where they restore enough buffer to finish the route. Tier 2 introduces a modified savings heuristic. The classic savings idea merges 2 routes when the merge reduces travel distance. For electric vehicles, a merge is only accepted if the new combined route remains feasible under battery constraints. If infeasible, the method must either reject the merge or insert a charging stop. The savings value measures how much distance is saved by connecting 2 customers directly instead of returning to the depot between them. This simple metric is powerful for constructing routes quickly. In electric routing, it must be combined with feasibility checks so distance savings do not create battery failure. This figure summarizes the heuristic steps. Start with 1 customer per route, compute savings, and merge routes in descending savings order. The critical modification is the feasibility check. Before accepting a merge, verify that the vehicle can travel the new sequence with its battery, and consider inserting a charging station when needed. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include savings heuristic EVRP. You will notice logic related to route charging. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails, so iterative logic stays stable and does not drift. If feasibility is enforced with penalties or repair steps, confirm the penalty scale is large enough to prevent invalid outputs from looking attractive. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, you can see the implementation details in action. You will notice logic related to route charging. As you read it, focus on the sequence of steps and which variables are carried forward because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. This figure illustrates swarm search concepts adapted to routing. The method balances exploration of new route structures with exploitation of good route patterns. For electric routing, feasibility penalties are essential. Candidates that require more energy than available, even with charging, are pushed away by large costs in the fitness function. Tier 4 reframes routing as sequential decision-making. The agent repeatedly chooses the next destination and receives feedback. A useful state includes current location, battery level, unvisited customers, and current time. Actions include going to a customer, going to a charging station, or returning to the depot. This figure shows the agent and environment loop. Through many simulated episodes, the agent learns which choices lead to feasible, low-cost completion. The reward design is crucial. It should penalize distance and time, strongly penalize battery depletion and infeasibility, and reward successful service of all customers and safe return. This slide focuses on Tier 4, Agent-Environment Interaction. Key points shown are: the agent learns a routing policy through simulated episodes. Operationally, use these points as a checklist, confirm the definitions match your data, confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. This figure represents the fleet-wide energy simulation concept. The twin connects vehicles, charging infrastructure, and environmental conditions. A practical outcome is what-if analysis. You can test the effect of adding chargers, changing battery sizes, or shifting delivery windows, and then measure service levels, energy use, and operational cost. Tier 6 uses decentralized multi-agent logic. Vehicles bid on tasks based on marginal cost and current energy state. Charging stations can also be modeled as agents that offer time slots and prices. This creates a market-like coordination layer that can reduce congestion and improve resilience. This figure shows decentralized negotiation. Instead of one dispatcher assigning everything, local agents coordinate. This can improve robustness when disruptions happen. If one charging station becomes unavailable, nearby vehicles can negotiate alternative plans quickly without waiting for a centralized recomputation. This slide focuses on Tier 6, Decentralized Charging Negotiation. Key points shown are: agents negotiate tasks and charging in real time. Operationally, use these points as a checklist. Confirm the definitions match your data, confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. This figure illustrates the collaborative workflow. The goal is trust and practicality. The human provides knowledge that is hard to encode, while the system provides fast optimization and consistent feasibility checks. Together, they create plans that are both efficient and operationally realistic. This slide focuses on Tier 7, Human and Artificial Intelligence, Collaborative Workflow. Key points shown are: human constraints plus rapid re-optimization yields robust plans. Operationally, use these points as a checklist. Confirm the definitions match your data. Confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. The multi-objective form aggregates cost, carbon impact, and fairness into a single weighted objective. The weights represent management priorities. Changing them shifts behavior, for example, favoring greener charging times or distributing difficult routes more evenly across drivers. This figure illustrates green and fair routing. One practical mechanism is to use real-time grid carbon intensity to schedule charging when renewable supply is high. Another mechanism is driver fairness. By tracking workload over weeks, the system can avoid repeatedly assigning the most difficult routes to the same drivers, improving retention and satisfaction. Tier 9 discusses quantum approaches. The routing problem is computationally hard, so alternative paradigms are explored. The idea is to compile the problem into a quadratic, unconstrained binary optimization form. Then a quantum annular can search for low-energy solutions that correspond to high-quality routes. The energy function combines linear and pairwise interaction terms over binary decision variables. In this view, a candidate route plan corresponds to a binary configuration. Lower energy means lower cost plus lower penalties. So the optimization seeks configurations that satisfy constraints while minimizing the objective. Constraints are enforced using penalty terms. The visit once penalty pushes the solution toward visiting each customer exactly once. If a customer is visited twice, the penalty grows and makes that configuration undesirable. This is how constrained routing can be expressed in an unconstrained quadratic objective. This figure summarizes the quantum annealing concept. The annealer explores the energy landscape using quantum effects. In practice, performance depends on encoding size, penalty calibration, and hardware constraints. Even when not fully optimal, these methods can provide useful near-optimal solutions for difficult instances. This slide focuses on Tier 9, quadratic, unconstrained binary optimization, and quantum annealing. Key points shown are: constraints become penalties, and the annealer searches the energy landscape. Operationally, use these points as a checklist. Confirm the definitions match your data. Confirm constraints reflect real limits. And confirm reported results are consistent with the scenario and the objective. The key lesson is that electric vehicle routing is routing plus energy management. Battery constraints, charging time, and infrastructure availability make feasibility central. The tiered toolkit offers a practical path: exact modeling for rigor, heuristics and learning for scalability, digital twins and autonomy for robustness, and value and quantum extensions for the next generation of systems. This slide continues the structured explanation of electric vehicle routing with charging constraints. Focus on the operational meaning of what is shown and how it affects route feasibility, energy use, service reliability, and total cost.